Okay. So Kirchhoff's first law states that the sum of current entering a junction is equal to the sum of current exiting the same junction. In fact, let's write leaving so you guys can remember that better. Right, kids? Now, Kirchhoff's first law basically follows the law of conservation of charge. That's a physics law that cannot break, so you guys need to remember that. Alright, kids. Now, let's look at the thing here. For example, there are different wires coming out of the junction, any junction for that matter of fact. This one is going at 3 ampere. This one is going out for 4 amperes. This one we want to find. This one is 0.5 amperes. This one is 1 ampere. And this one is 2.0 amperes. So we want to see what's really happening, okay? So we're gonna basically write entering should be equal to a sum of current entering sum of current, right? So what you're gonna do is you're gonna add all these. This is entering. So I plus 3 plus 1, and on the other side 4 plus 0.5 plus 2. So this will be 4. This will be 6.5. So I will be 6.5 minus 4. So that's going to be 2.5 ampere. It's very simple. And this is how it's done. All right, kids. Any questions? Please let me know.
No.
Write it down, please. And then let's go forward. All right, kids. Should I go forward, please?
Yes.
Okay. Now, let's check this one out. The next law is the Kirchhoff's second law. The second law is also known as the voltage law. Now what it says is that the sum of EMFs around a loop in a closed circuit is equal to the sum of potential differences around that loop. Now this is a tricky one, but with an example. But first let's write what it belongs to. So write a note that second law follows law of conservation of energy. For example, you have a couple of cells right here, and then you have two resistors. Uh-oh. And then you have another cell, but this cell is, if you look at this, this is against the other two. Now two resistors again, and then connected to the battery. Now let's call this EMF 1, let's call this EMF 2, let's call this EMF 3, let's call this R1, R2, R3, R4. Also, let's call the voltages across each of these V1, V2, V3, V4, like that. And the current in this circuit is I. Now, what I want to tell you is that obviously this is positive, this is negative. So the positive terminal of any cell should be connected to the negative of the next cell. But if you look at here, the positive is right here, but then positive is connected to positive, which means this cell is against the flow of current. And we're gonna keep that in mind. Now what to do next is you're gonna write sum of EMFs will be equal to the sum of potential differences. Now let's write EMF1 plus EMF2, we're going to add them together because they are correctly connected. And we're going to subtract EMF3 from this because that is against it, equals to now V1 plus V2 plus V3 plus V4. And if I expand this formula, then V1 is the current into R1, V2 is current into R2, V3 is current into R3, and V4 is current into R4. So you can basically, what it means is that in a certain loop that you go around the circuit like that, so you just need to check which batteries or cells are connected one after another, which one is opposite, and then you can create this equation. If you have any questions, please let me know. Everything's clear, kids? Asma, do you understand? Shazib, Furqan? Okay. Right. Write it down, please. बेटा मैंने ना नहीं खाना, ये मैंने भी खाना खाना है तो ये तुम खाओ। नहीं आप ही लेके आए। मैंने वाकई नहीं खाने थे, वरना मैं खा लेता। तुम लोग खा लो बेटा, ये मैं खाता ही नहीं, मुझे पसंद नहीं। Alright, is it clear everyone? If you've written, should I go forward please? Alright kids? Now obviously when you're looking at DC circuits, you want to know about series and parallel. And by use of these laws, we have created some more formulas. Series basically means that you have connected a source and some resistors, one after another, like that. This is EMF E, the current is going I, and each resistor is R1, R2, R3, and the voltages across these ones are V1, V2, and V3, like that. In parallel, we have each resistor connected, or say it's branched out like this. If this is EMF, each one will have the same voltage. Let's call V1, R1, V2, R2, V3, R3, and the current is I here, and each individual branch will also have its own current because it's going to divide. Now, just remember that in series, current in each component stays the same, but the EMF is the sum of all potential differences. Now, obviously, we know V is equal to IR. So total resistance will be IR times I, which is equal to EMF. Then this will be I times R1. This will be I times R2. This will be I times R3. Because current is the same in each component, so it's going to cancel out, leaving you with just one formula that in series you can find the total resistance by simply adding them together, like that. you have any questions, please let me know.
No, sir.
This derivation is included in your course, so they can ask you this. Then in parallel, voltage in each branch is same, which means voltage across, which means that the EMF will be equal to V1, will be equal to V2, will be equal to V3. But however, the total current is the one that gets divided, so we can add the current in individual branches to get the total one. Then, as we know, we can write I as V upon R, so we can replace it. So voltage over total resistance will be voltage over R1 plus voltage over R2, because voltage is same for each of these. Voltage is going to cancel out. That means that now we can get a formula. The total resistance can be found out if you add the reciprocals of each resistance and then you take the reciprocal again. Is it clear, everyone?
Yes.
Derivations included. Please write this down carefully. And if any point you do not understand, let me know. Then we'll do some of the questions in this one. All right, kids, go forward then. Now, I don't know, I have space or not. I have to go to the next page, so you can write it down, take 2 minutes out, and let's see. Okay. Now let's look at an example and see how we can basically manage these circuits. It's pretty simple. Let's look at example from here. So you have a network of resistors. There's a positive, negative. Then you have 2 resistors. And then at the bottom, we have 2 more. Let's make another one just to make things more complicated, like that. So this one is 40 ohm, this one is 20 ohm, this one is 60 ohm, and that one is 40 ohm. That one is 96 ohms. And the voltage, the EMF is 6.0 volts. Now the question, the first part of the question is, show that the network of resistors have a total resistance of 440 ohms. So this is the question. Then in the next part, part 2, they say calculate the current in 60 ohm resistor. So these are the two questions that we got to. Now, whenever you're dealing with certain questions like these, there's a way that I use to think, and I don't know if it's for you, but if you like it, you can follow this. I always tend to solve the innermost circuit, which is this one. So call this one. And then I go to the outer one from that. So let's call this 2. And then I solve the other branch, 3. And then I solve them together, 4. So I'm going to take them in 4 steps. Is it clear, everyone?
Yes.
If you look at the first one is a parallel circuit. So in parallel, I got to remember that 1 upon R will be equal to 1 upon 60 plus 1 upon 40. All right.
Yes.
Now, what you do is when you solve this, obviously 60 upon 40, you can simply use a calculator. Do that. Don't waste your time. It's pretty simple, though you can take 240 as your LCM, but why do that? Just take 1 upon 60 plus 1 upon 40, and then take 1 divided by answer, take the reciprocal, it will be 24. So you get 24 ohms. Then check that the second portion is a series circuit, so with this one. So the answer for the first one and the 96 is basically the series, which means that the total resistance now in series you simply add them. So 24 for the parallel section plus 96. So I think that's going to be 120. So step by step we're going to do this. The third one is the innermost circuit, which is also a series circuit, as you can see. That's the second branch one. So you can do R, simply add it, and that's going to be 40 plus 20, and that's 60 ohms. Now, obviously, 2, circuit 2 and circuit 3 are in parallel. So in the fourth step, we got to solve the parallel circuit again. When I use the parallel equation, which is 1 upon R equals to 1 upon 120 plus 1 upon 60. So then use the calculator again. 1 divided by 120 plus 1 divided by 60, and then take the reciprocal again. So it's going to be 40 ohms, and that's how I have shown that the total network is of 40 ohms. If you do not understand something, please let me know. So generally, I find this the easiest way to just segregate each and everything and then move it to my liking. Keep it to the side. Wait. Alright, kids. Now, in the next one, if you see, they say calculate the current in 60 ohms. So, if I were you, I would segregate all of this. You see, the 60 ohm has a total like section of branch. Second. Sorry. Okay, so this is 60, as you can see. This one is okay. What did I do here? Okay, this one is 40, and then snap so bad. Okay, and then you have 96 here as well. If you notice that this whole branch, obviously because each branch in parallel gets the same voltage, it means the whole branch here is gonna get 6 volts of total voltage that is right here. So you guys need to remember that. Now there are a couple of formulas that we can use. First of all, we'll find what is the total current in this whole branch. So we're going to use V equals to IR. The voltage is 6, current I, and the resistance in 2 was 120. So I'm going to use 120 here. And I then will be 0.025 amperes. So I know what is the total current. Is it clear, everyone?
Yes.
Now from this, there are two different methods that I can use. So for example, if I use method 1, which is just formulas, so you can use V is equal to IR again, and then use the current of 0.025, and because the whole circuit was 24 ohms, these two, so we can use 24 here, and we're going to get the amount of voltage that we had. So the 0.6 volts, which means this circuit, basically this gets 0.6 volts, and this also gets 0.6 volts because they are in parallel. So in parallel, voltage is same. Then I'm going to use V equals to IR again, and now I have I want to find voltage. So I have 0.6 volts, again 60 current I want to find, and that is 60. So 0.6 divided by 60 would give me something like 0.01 amperes. So it will get this. There's another method that you can always use, but that's up to you if you like it. This is a ratio method because you guys need to understand the resistance and current are inverse ratio, so we have to use inverse ratio. If I say 24 ohm gets a current of 0.025 ampere, then what will be the current in 60 ohms? Now, when you have inverse ratio, you do not cross multiply, you direct multiply, which means you're going to multiply this with this, and you're going to multiply this with this, and put them equal. So if you do that, it is going to be 24 times 0.025 equals to 60 times x. You're going to end up with the same answer as the first one. This is the method for inverse ratio. So whatever you like, you can do that. If you have any questions, please let me know.
No, sir.
Please write this down then. Just remember, you can also write on the side a note that inverse ratio means that you have to multiply things like do not cross multiply, multiply directly to each one, like multiply the things in front together. All right, kids. Should I go forward, please?
Yes.
The next concept is the internal resistance. Now, internal resistance, let's write that and define it as well. Internal resistance is basically the resistance within a cell or a battery that causes some voltage to be lost. You can also write energy to be lost, because what happens is when you look at any cell, cells basically look like this. In real life, they're also like this. They have a positive terminal on this side, there's a negative terminal on this side. Within the cell, obviously, you have a chemical energy stored. Those who have taken chemistry, they already might know this. So the real exchange between this is that the chemical energy basically converts to electrical energy plus some heat, that is the loss in this. All right. Now in physics, what we do is to simplify the diagram. Now there's not an actual resistor inside. We just denote it with the resistance. Like you don't have any small resistance there. We just draw that to explain that there is an internal resistance R in this. This is EMF, and the whole basically cell is made like that. So this one, kids, from this to this, we have uh, EMF. From this to this, we have voltage lost. And outside, what you get remaining is the terminal potential. Terminal potential means that it is basically the amount of voltage that you receive for anything that you put outside. Now, like anything, it also follows the law of conservation of energy. Like we can say total energy then will be equal to energy supplied by supplied at the terminal or terminals plus the energy lost. Obviously, the total energy would be related to the EMF, because that's the whole thing that is being supplied. Let me change the color so it's more clear. That is the EMF. This is the voltage at terminal that we get plus the voltage lost. Now EMF is written as E. The terminal voltage is written as IR. I'm going to explain how. Plus the the voltage lost is current into small resistance. So generally we want to remember it as, you can take I as common, so it will be R plus small r. So where is this big R coming from? It's basically when you attach a battery or a cell, basically a cell with anything outside with a resistor like that. So this is the load resistor. We call this as load resistor, which means whatever you're putting in the circuit to use. This is the EMF, this is R, and that is the current. Is it clear, everyone?
Yes.
Now in this one, I'll just write every word. R is the internal resistance in ohms. Capital R is the load resistance in ohms. I is the current and E is the EMF, like that. Get it?
Yes.
Right. The final thing that we're going to do with this one is the graph of power versus load resistance. So you got to have power on the y-axis, you got to have load resistance on R. Now you don't need to learn the formula for this graph, how it is derived, just need to learn the shape. It's like this. So you guys need to remember a very important part, and that is that the maximum power output will be when the load resistance will be equal to the internal resistance. Is it clear?
Yes.
I'll write it down as well so you don't forget. So please write the yes, yes, Daniel. So the maximum output from the battery is when load resistance is equal to the internal resistance. Usually MCQs would come, so you can directly pick this up. I've not seen a question of this in paper 2 ever. Alright kids,
Yes.
write it down please. All right, kids. So we're done here. We just need to do two more small topics in this, and then we'll do the worksheets for the whole electricity because they're so interrelated that I didn't